We finished last week talking about the properties of solids, and I finished with the phase diagram for some substance which we think we are very familiar with, namely with the common ice. And I am showing that phase diagram again. As you see, there are many different kinds of ice which are present. And I'm showing this diagram in order to focus your attention on the fact what are actually the most important differences between the liquids and the solids. And let's think about the liquids. If we have a container with the water, liquid argon, a benzene, or whatever, then there are important macroscopic properties of those substances, like that a particle out of which they are built, they can flow, move from one point to another, and if those particles are exchanged or moved, macroscopic properties of a system are in some sense the same. The other important properties are that if I have a huge container full of the liquid, then all the points within that container are equivalent. What does that mean? That means that if I'm having a huge container like an ocean, and if I put my finger in one particular point and I move 2 kilometers away, then there are no macroscopic differences between that water. And the final property, which is important for my talk, at least for that part of the lecture, is that in the liquid there are no privileged directions. Those three properties in some sense define a macroscopic substance, which we call liquid. And sure, in nature there are many substances which are commonly called liquid, but which will not actually fulfill all those three conditions. For example, if you are watching me on your computer screen, there is a certain probability that you are watching me on a liquid crystal display. And that liquid crystal display is a liquid crystals, substances discovered at the turn of the 20th and 20th century. They are, in sense, both liquids and solids. They flow, but they have a privileged directions, and not all the points in the liquid crystal are equivalent. So let's look at the solids. The solids are substances where the constituent particles sit on a given points in the space. In most of the cases, that structure which arrange those positions in which the particles sit are one of the crystallographic lattices. So the position of the particles are well defined, and the particles do not move away from them. If they execute a motion, they move only in the neighborhood of the particular site. The other property which distinguishes solid from the liquid is that the different points in the unit cell, and I shall define the unit cell in a second, are not equivalent. If the solid is built up as one of the permitted by the mathematics lattice cells in a three-dimensional space, then they not necessarily look like the simple drawing on the page of your high school problem book, namely the square or cubic lattices in 3 dimensions. They might have a different geometry, and the geometry is occasionally so complicated that at different points within the given, this lattice consists actually of fragments, and those fragments have a complicated geometry, and those fragments repeats themselves in the space. Those elementary fragments, which then repeats in the space, we call a unit cell. And it is a mathematical exercise to prove that if I know all the geometrical properties of those unit cells, and if those unit cells repeat themselves, filling up the whole space, then the properties of that particular unit cell repeats itself if I cut a larger volume of the lattice and so forth. And the points within the unit cell are not necessarily equivalent. There is a full science of a lattice structure which deals with the consequences of the fact that the unit cells can have a complicated geometry, and the consequences of those geometrical intricacies of the unit cells are responsible for many macroscopic properties of a crystals. For example, they are responsible for the properties of the semiconductors, which are used, which are the heart of the contemporary electronics. So in a certain sense, without the knowledge of that fact, we wouldn't be able to build up contemporary devices like transistors, and there's just no way how we can imagine the life nowadays without the transistors, or the other electronic devices like those solid state memory devices which sits into the pen drives, etc., and also the underlying structure of your screen on which you are watching this lecture. And the third difference between liquid and solids, to keep with the number of those 3 properties, is that there are privileged directions in the crystals. If you have a cubic crystals, that's very easy to see that there's each of the directions along the edges of a cube are equivalent. But if you have a hexagonal crystal, then those 2 directions which are in a hexagonal plane are different from that axis along which is perpendicular or at angle to them, the z-axis that we used to say. And that non-equivalency of the directions in the crystalline lattice play also tremendously important role in the physics phenomena which occur in the crystals. If you look at the magnetic materials, those materials which do have magnetic properties, then most of them is related to the fact that the magnetic ions sit on a certain axis in a crystal and not on the others. So for example, many magnetic crystals looks like the arrays, bundles of a one-dimensional lines along the magnetically active ions are located. And each of these lines, to a certain extent, and for magnetic properties, to most of the facts, behaves as a one-dimensional object. So we have those 3 differences. And let's ask us now the question, what is the main reason of those differences. What physical property is actually responsible for the differences between liquids and solid, as shown on this little table. And what distinguishes these three different states of matter? And the answer is there is a one property, and that is a property which we call a symmetry. And we have started our lecture, as you remember, with the discussion that there is a difference between the symmetries in the organic life and the non-organic life. And we discussed the symmetry a little bit. And I would like to spend some time today discussing the symmetry consequences in distinguishing between liquids and the solids. And that brings us to the part of our talks on crystal properties or solid properties, which has a traditional name, elasticity. That is a science which is extremely important and which in some sense grow up as an independent branch of science, similarly to hydrodynamics. And because that is the part of our physics which is responsible for the fact that we can build devices, that we can build houses, well, whatever, because when we construct something from a material, we have to be able to estimate how sturdy it will be, depending on what kind of interaction that structure will be supposed to survive in its life. So let's start with discussing a very simple system, namely, imagine we have a one-dimensional solid. We have the particles, atoms, or molecules, which I have denoted as a well, what the hell is this color? Green, or, well, it doesn't look like very green on my screen. Anyway, those little dots, and they sit at a certain position, the lattice side, which are labeled by a position X along the X-axis. So if I look at these two particles, that one sits on a position X1, and that sits on the position X2. But the lattice is, this particle which formed the lattice must have some kind of interaction between each other, because if they didn't have the interaction, then there will be no reason that they keep exactly certain distance from each other. Like we are now asked to stay 2 meters, at least 1.5 meters or 2 meters from each other in this social distancing procedure imposed by the pandemic regulations. Like there must be some rule which keeps this green atoms or particles or molecules at a certain distance from each other. And I have depicted those rules which keep them away by a spring. For what are those particles? We know that they interact, and when they interact with you recall, the van der Waals potential, then basically, if I have two of such particles, they will sit with respect to each other at a distance which roughly corresponds to the minimum of the van der Waals potential. So what happens now if I apply a force, if I push one of those green particles by a certain external force? Well, if I push them, then those fictitious springs which keep the arrangements of our particles, they will be under, they will also suffer a certain force applied to them. So they will, as a result of that, those green particles will move away from that from their position x1, x2, and so forth. And I shall call those position equilibrium position of the particles. So when they move away, situation will now look like this. Our particles will still in the one dimension, and they will move a little bit. So that particle, for example, a particle number 1, has moved a little bit from position x1, and that means that its new position will be x1 plus certain deviation from the equilibrium position, which I have denoted as a little u. So I have put up a restriction on my positions, namely such that the difference between the x2 and x1 is equal to a, between x3 and x2 is equal to also to a, and so forth and so forth. And I shall call that length a lattice constant. And in one dimension, there is no other symmetry element than the lattice constants. It tells me that the atoms are forming a periodic structure, and the periodicity of that structure is having a length a. So that is very easy to calculate that the total length of that one-dimensional structure, denoted as a L sub 0, is just the number of lattice sites times the length. And that is the structure. And in the 17th century, there was a physicist, British physicist, Robert Hooke, a contemporary to Isaac Newton, who had concluded that if the force applied to our lattice is not too strong, then the particles move away from the equilibrium positions, but not too much. And if they move not too much, then the difference between the old and new position of the particles will be just proportional to that displacement which I have denoted by a little u. So the relation between the force and the displacement will be linear. There will be coefficient which converts the unit of u into units of force. Force is measured in newtons, u is measured in meters, so that this coefficient k is just the newtons divided by meters, and that law is called the Hooke law. Robert Hooke was actually an interesting individual. He was a secretary of a Royal Society and was very busy with preparing the experiments for the Royal Society, for he was basically a poor man. And he also is, as historians are trying to tell us, was the first individual who guessed what is now called the Newton law of gravity. But that's the other story. So that is a Hooke law, which says that the displacement is proportional to the force. All right, so let's look at the situation again. We have our green points connected with the springs, and we apply a force and we displace, but we can displace those particles not only applying a force such that the displacement is identical. We can apply the force such that the first atom moves a fraction of a centimeter, a second move a fraction of a millimeter, but in the opposite direction, a third half of a centimeters, yet again in the other direction. And also, the force might be time dependent. So the displacement of the atoms can be not only the function of a position, but also a function of time. I put a little arrow on top of this U, for I am assuming that what I write here might, in some sense, be generalized to more dimensions. And as we see, then we cannot use only a scalar variables to describe displacement, because we have to answer the question, if the applied force acts in the x direction, what it might be the displacement of an atom in a crystalline lattice in the z direction. So we must use the vectors, objects of a geometrical structure. So that is just to remind you about that complication. So I have depicted the displacement as a little arrows, and my Hooke law is now quite simple. A force is proportional to the displacement. If I will put up this law into the Newton equations, which describe the dynamics of the lattice, which is a linear equation, but they're fairly complicated because atom X1 is connected to atom X2, and atom X2 to X3, and so forth and so forth. So I will have a complicated linear equation to solve, and that is possible. So if the force is periodic in time and space, I can solve my Newton equations exactly, and the solution is that the displacement as a function of position and time is a simple trigonometric function, is a simple cosine function with some coefficient. There are two coefficients in the brackets, which one is the wavelength, denoted as a lambda, and the other is a velocity, VL. That coefficient here tells us what is the special extent of the lattice deformation described by displacement, and this coefficient denoted as a V with subindex lambda tell us what is the velocity with which this excitation moves along the crystalline lattice. It turns out that this velocity is equal, is just lambda, is inversely proportional to the wavelength, and in the numerator we have a ratio of the constants k, this Hooke constants from the force displacement relation, and rho is a density of the particles along the axis, x. So I have everything here, and the important thing is that in the first term in the bracket, and also in the second, the lambda sits in the denominator. So if we have excited the excitations in the lattice described by that equation, then the lattice is very asymmetric. There is no symmetry in it. When we move by a distance a, the lattice constants, we do not come back to the same structure of a lattice, and the things are pretty disordered. But what happens when the wavelength of that excitation, a parameter lambda, goes to infinity? When lambda goes to infinity, then the expression in the bracket vanishes, and when it vanishes, a cosine is equal to 0. The argument of a cosine is equal to 0, so the cosine of 0 is equal to 1. So we get the expression that in a lambda going to infinity limit, the displacement is becomes constant. When it becomes constant, that it corresponds to motion, to the translation of a whole lattice by a distance u0. Nothing changed because we have shifted the whole thing by the distance u0, so we cannot tell what is the structure now. The structure now doesn't change anymore. We shifted the whole thing. So we have restored a translation symmetry of that lattice. And the situation can be this kind of a situation where one of the possible motion of the lattice at the wavelength going to infinity restores a symmetry which is broken by the lattice itself, is in physics called the Goldstone mode. And that is the extremely important, one of the most fundamental concepts in the elementary particle physics, which can be visualized so simply for a simple one-dimensional lattice. What is then this distortion of the symmetry? Now you see the picture of the broken translation symmetry. That line is completely broken. It's no longer translation. Even if the line had been painted from Warsaw to Krakow, then because of the little hump, because somebody avoided painting that piece of wood, is breaking the symmetry. But if the painter made that bump U with infinite wavelength, that bump will be extending by itself from Krakow to Warsaw, and the translation symmetry of that one-dimensional system will be completely regained. So we had managed to learn a little bit of a complicated physics, and we shall continue with the elasticity further on. We have the same picture again. Okay. And the reason why I'm showing it again is that since I apply a force, the particle moves, so that force does some work. And if that force does some work, then it stores the energy in our lattice, one-dimensional lattice. So if I have a displacement U, then it is an exercise in elementary calculation to show that the total energy of that lattice, of that displacement, is 1/2 of a coefficient K times U squared. And that is a very important relation, so kindly keep it in mind, because we will use it in a second for an exercise from the biology. I'm aiming at calculating for you what is the maximum height from which we can jump without breaking our legs. All right. If I apply that force, then the length of the lattice, remember L0 was just the number of sides times the lattice constant, changes by a little delta U, and that little delta U, the delta L, and that delta L is essentially nothing else than the sum of all the displacement of the particular points. All right. So let's now leave the one-dimensional world. We are not really living in a one-dimensional world. So let's look at the situation in 3 dimensions, and let me first look at on the cylinder, to which I have applied a force which pulls it in both directions. If I do it, then the length of the cylinder changes by a delta L. And if I do the opposite, namely if I press the cylinder with the force from a top or from the bottom, then the cylinder shortens a little bit by a delta L. if the materials out of which the cylinder is made is subject to the Hooke law, then this is easy to imagine that there must be a similar to our lattice relation between the change of length delta L and the force which is applied to it. And in a three-dimensional world, the physicists and engineers try to use not a dimensional number delta L, because it has a dimension, but the dimensionless change of length, namely the delta L divided by L0. And that kind of a quantity has its own name in physics. It's called strain, and is conventionally denoted as a little epsilon. And similarly, if I have a cylinder, not the one-dimensional lattice, then, as we remember from our talk about the liquids and solid and gas, the force applied to the area here is divided by that area is just what we used to call the pressure. And in the elasticity theory, an analog of a pressure, that force divided by the area of my sample, is called stress. And the Hooke law defines a coefficient which previously I labeled by K, but in elasticity theory is usually called a capital E or a capital Y. It's called the Young modulus, and it is simply the relation between a stress and strain. So we have to divide this. We have to divide these two quantities by each other to get the modulus, and out of that comes a simple redefinition of a Hooke law, that the stress is linearly proportional to the strain. This is a stress-strain relation. And if I plot that relation on a plane where the x-axis is just the strain and the y-axis is stress, then I have a set of straight lines. And I have plotted here the Hooke law for various substances. For example, as you see, the Young modulus, well, because it has the dimension of pascals, so it's measured in pascals. The biological tissues have a Young or modulus, which is 10 to the 5th of a pascal. The common rubber which is easy to check by yourself that the Hooke laws is really true, is slightly larger, 10 times larger. The plastic materials, like the bottles, like that material out of which the mineral water bottles are made, is 10 to the 9th of the pascal. And the construction material of our civilized world, namely the steel, has a coefficient 10 to the 11. So it's 6 orders of magnitude stronger in that sense than biological tissue. But what is happening when we will deform the body if the strain becomes larger and larger? Is this law holding up to infinitum? No. If we will extend the strain, then the relation between stress and strain becomes much more complicated. And this is roughly the drawing of what is happening. Initially, we still have a Hooke law, a straight line, and then eventually at a certain value of a strain, or if you want at a certain value of a stress, something is happening, and the curve becomes essentially flat. That point is called the yield stress. The substance is deforming without actually or very little applied stress. There must be something what is happening inside of the materials that when the stress is sufficiently high, something in a quotation breaks in. The question is that the materials microscopically consist of these lattice points sitting in a geometrical structure. And geometrical structures cannot just simply break, disintegrate. They, in some sense, disintegrate when we apply too much temperature and if the crystal melts. But if we just apply the force, they do not disappear. There's something which is happening within that geometry. And that point was not well understood until the beginning of the 20th century, when people have found out that the crystalline lattice may undergo a certain peculiar transformations which breaks the geometrical, or in a more precise language, topological structure of the crystalline lattice. Topology is that structure of a geometry which is independent of a deformation. So the topology is being break. And there was a great Italian mathematician, Vito Volterra, and you remember we were talking about the Vito Volterra on our short discussion of a population dynamics when we were talking about the van der Waals, when we were talking about the logistic map and chaos, and Vito Volterra had proposed what is happening in a crystalline lattice at that particular point, and invented, together with the Dutch physicist Burgers, a concept of a dislocations, that there is a geometrical change in a crystal which facilitates that particular stress-strain relation. And when we keep going with applying higher stresses or larger deformations, then the stress-strain relations start to become like this. It looks like that all over the sudden, the material becomes stronger again. And this is called a strain hardening. We harden to some certain material, but the relation between the stress and strain in real materials stops to behave like this. And that is what the engineers are afraid of when they are building, for example, a steel construction on which the buildings are hauled. And one of the dramatic consequences of this seemingly increased strain, which leads to another phenomenon which is called the necking, that is that the material becomes thinner in the middle. We apply the stress and it's not only extended length, but also becomes thinner and in the perpendicular to the force direction. And that was what had happened to the steel skeleton of two towers in New York, when under the tremendous amount of localized energy, the lattice on a certain part of the building, the steel lattice in a certain part of the building underwent this deformation as shown on the drawing, and eventually there is a point which is called a fracture. The construction had collapsed. So this is basically extension of a Hooke law, and engineers are pretty good nowadays in having laboratory measured properties of a given construction materials, construct a construction like a building, a bridge, or whatever, which can operate at under the weight, and not only the weight of the, say, trains or people walking on it, but also by a blowing wind or falling snow and things like this. And they can use this particular property to proceed with our construction. This is very tricky if you think that these giant buildings nowadays constructed, they have inside a metal construction and a concrete construction. So they have a metals and a ceramic material, kind of a material. And on the side, they have a glass plate. And they had to keep those glass plates with the same kind of elastic properties so that the building, when they move, shakes, and so forth, will not shed the skin, so to say, shed the glass cover, and that would be incredible disaster. So we know a little bit about the stress-strain relation, and just a few names. If I pulled up the cylinder, the deformation is called tensile, and when I apply the force trying to shorten it, then it's a compression. But now let's look at the node of the cylinder, and let us look at the block of a material in the form of a cube. If we look at this cubic material and we apply the force F in this direction, which I still keep on calling X, and let me hold the bottom of the box hold, or apply the same force F in the opposite direction. Then this is what the engineer will call shear, and the upper layer of the material will move away, and that will be held fast. So now we have a complicated situation. The length of the cube was L0. Now there is an increase of that direction, delta L, but there is a different change of the length of what was previously vertical edge. And we have a complicated situation, for we apply a force in one direction, but the deformation might happen in the other direction. And since we have 3 dimensions, we might envisage a situation where we apply the force in one direction, and we may have a reaction of the materials in all remaining 3 directions. That means that the deformation the strain cannot any longer be just a number, because that number can only tell me what is happening in one direction. But I'm able to answer what happens with the lengths in the vertical direction to the direction of applied force. And that means that we have to use a special mathematical description to do this. And I'm not going to deal with this more. I will just write you that, for example, we can have a stress in the direction X and X, and the direction X and Y, and the direction X and Z. And it will cause the change, the strain in the direction X and Y, and 2 perpendicular directions. And I can write many of them, since there is at most 9 of those different stresses in 3-dimensional world, and 9 strains in 3-dimensional world. that the most general Hooke's laws, which I can write, is a relation, the little I and J stands for X and Y, so is K and L, and the relation of that object with the nine numbers sigma to the 9 numbers epsilon is related by a giant table of the numbers which generalize the Young modulus. And the property of the giant table depends on the microscopic properties of the crystal, of the lattice, of the material. And if this is a homogeneous and completely isotropic material, then we can prove mathematically that there are only 2 independent E coefficients. This giant 3 times 3 times 3, that means 9 times 3, 27 times 3, there's a 60 and 81 numbers. In general, they reduce to these 2 numbers, which are called Lamé coefficients, lambda and mu. Lamé was a French mathematician who was one of the first who had used the complicated geometrical language and methods to describe, to solve the differential equation of elasticity. And these 2 coefficients, they have to fulfill certain conditions. The coefficients mu, which is called the shear coefficient, must be always larger than 0. But remarkably, the symmetry conditions do not tell us what is the sign of a coefficient lambda. It can be negative or as positive. But it just so happened that there are essentially no materials for which coefficients lambda is negative. There are coefficients, peculiar coefficients with the negative lambda, but I'm not going to discuss it, why that so happened. And if we will try to describe the isotropic homogeneous medium without this complicated relation, then we can calculate what will be the change of a volume of the material under the pressure, and that coefficient which tells us that change is called, again, Young modulus, and it is given as a sum of lambda plus 2/3 of the mu. So that's the Hooke law in a 3-dimension. And then the energy stored in compressed or stretched isotropic body is very similar to what we had for the Hooke law for our lattice. Is proportional to the square of this elongation or compression, and what replaces the length, the spring constants K, is the product of the Young modulus times the area of the sample divided by its length. All right, so now we have the application from biology, namely we are going to talk about the bone fracture. This is just an example why I bother you with all those complicated engineering concepts. And we have our leg bone, and let's assume that it has a length L, and the cross-section is equal to A. This is approximate description of a bone, but let's use it. And for a average individual, that cross-section is a 6 centimeter square, and the length of the L0 is about slightly less than 1 meter, and that's for the 70 kilograms person. So let's use our knowledge of elasticity to calculate a few things. I really remind you the stress-strain relation. Stress-strain relation is that ratio. So now I can assume I know the stress at which the bone breaks. Then the force at which it will break is out of the stress-strain relation given by the following expression. If I now do a little bit of algebra, then the change of a length of a bone is that given by nature value of a stress at which the bone cracks times its length divided by the Young modulus. So the energy which is stored in my bone when the stress is applied to it turns out to be very simple, and it is the area length, that is what? That's the volume of the bone, divided by the Young modulus and times a square of the stress at which the bone cracks. So now I have to take the Wikipedia or any book on which has these numbers, and it turns out that the stress at which the human bones, actually most of the animal bones, breaks is the 10 to the power 8 of a newtons by the meter square, and that is of course 10 to the 8 of the pascals. And the Young modulus measured for the leg bones is 14 times 10 to the 17 newtons per meter square, pascals. So I can plug these numbers in, and having the knowledge that the cross section is 6 centimeters, length is 0.0 meters, so I have all the coefficients here, so I can calculate that energy, and that energy is 192.5 of a joule. In the leg, if we jump, we have 2 bones, because we land on 2 legs. Therefore, I have to multiply that by a factor of 2. And I'm sorry. And the energy which is stored in the leg of a person with the weight of the order of 70 kilograms jumping is then twice the 192 joules. So that is if I divided it by the mass of the 70 kilograms and the gravitation constant g, the gravitation acceleration g, then I calculate the height from which I have to jump in order to store so much of the energy in the bone. So it turns out that if I jump from the height of 56 centimeters, 60 centimeters, then my bone will crack. And everyone knows that we can easily jump from the higher, much higher heights without breaking our legs. Why that so happen? It so happen because we never apply a whole energy to the bone by changing our body. We are jumping out from the height, and then we change the shape of our body. We kneel or we turn, and that means that we dissipate part of that energy without applying it to our bones. But that is basically the limit from which our bones can stand if we do not anything, and that explains why so often we break our legs by simply falling on the ice. Because if when we fall off without any precautions taken on the ice, we do not change the shape of our body on falling, and that is roughly what is actually happening. So that was a short exercise of application of elasticity theory to the biology. And then now we are going to go into another part of physics, which plays important role in biology, namely to thermodynamics. What you see on that picture is a heat engine, steam engine, and that is in fact true, that the science about the heat and thermodynamics science, how the heat energy is being converted into work the other way around, and what are the consequences, was a science which originated with when the people built the steam engines. And there is a story who had built the first steam engine. As always, there are stories that ancient Greeks have something which looks like it's called Heron mill and things like this. But basically, the first steam engines have come out into existence in England when the British have chopped off all woods in the woods, and they didn't have much of the woods left for burning and heating up their houses. So they had to dig out coal, and they start building the coal mine. And one of the problems they encounter in coal mines was not so much lifting up the coal up from the pit, but basically what to do with the water, because the mine underneath is if left without any action taken, is flooded in a question of hours. So the main problem in the mine is to get rid of the water, and of course also to get rid of the gas, of the methane, which is there, but that's not the part of the thermodynamics. And anyway, so the engineers were building complicated devices to pump the water out of the mines, and eventually they came out with a steam engine. And usually the history tells that the first really usable steam engine was built by James Watt, and James Watt constructed the engine. But I'm not going to talk about the steam engines. I'm going to talk about the science of thermodynamics. And this is the only branch of physics where the fundamental law of nature, the law of conservation of energy, we owe to the medicine. The history, in some sense, we are now, in a sense, what we are doing now, giving to the biologists and the medicine people all those fantastic devices used in the diagnosis, from the stethoscope through the X-rays, computerized tomography, nuclear magnetic resonance, ultrasonography, and now positron emission tomography, PET, and finally, if we will master it, single photon emission tomography. This is just that we are paying a tribute to the medicine for formulating for us the fundamental law of physics and fundamental law of nature, the law of the conservation of energy. And the law of conservation of energy is in thermodynamics called the first law of thermodynamics, and actually has been formulated first time and in a proper sense, proper way, by Julius Robert von Meyer, a German ship doctor who on one of his trips over the equator was reading, I believe the ship was called Java, but I'm not sure I remember it correct. I might check for the next meeting. And Meyer was reading a book by a French chemist and physicist, Lavoisier. Lavoisier, as you might know it from a course of chemistry, was the man who understood what is the burning, right? That what is the role of the oxygen in a process of burning. And he had stipulated that actually the animals and the humans, when they consume the food, that the process of getting the energy out of the food by the living creatures is nothing else as the burning of something. So Mayer was reading the book by Lavoisier and realized that if that would be the case, then the concentration of the oxygen in the human blood should change. And he had a proof of that in the fact that the blood in our venous blood is much red as compared to the arterial blood in humans. And he realized that when he was crossing the equator, some of his soldiers got sick, and he had to restore to this famous, at that time, method of treating a fever, namely by bleeding the patients. That is from the field book of wound medicine of Hans von Gersdorf from 16th century, showing the points on which you can bleed the patient. So let's now go back to the Mayer. And he was bleeding patients and realized that the color of the blood was changing when they were crossing the equator. Once they were in a warmer climate, the color of the blood was changing, and that implied that the content of oxygen in the blood was changing. And that, what Mayer concluded was that in the warmer climate, you do not need to eat so much. Therefore, you are burning less oxygen than in the colder climate, and therefore he can concluded that there is a conservation law of what we wrongly called a force. And until the pretty late in the 19th century, what we nowadays call energy, physicists were actually called force, and they use different forces. There was a vital force and that force, other force. That's the energy. And when he came back from his trip, he wrote a paper. That paper was not accepted. And Mayer was fighting for his achievement, and that ended up very badly. He tried to commit a suicide, and that was unsuccessful, and he suffered a lot, and it was eventually closed in the mental asylum, and he died actually in the mental asylum. And his work and the fact that he had formulated the law of a conservation of energy for the first time before the British scientist and the brewer owner Joule has done, and Joule was for years considered to be the father of a law of conservation of energy, but that's not true. The father of a concentration energy of the conservation of energy was Julius Robert Mayer, and he died in 78, a completely unknown person, and he formulated the law of a conservation of energy. And now we are going to talk a little bit about that and about it. What is on this drawing is a post stamp issued by a German post to commemorate his 100 years of death in 1978. It was a 90 groschen at that time, Phoenix at that time. They didn't have euro at the time, so that is the stamp. All right. So we are now going to talk about the conservation of energy, and let's imagine for a second that we have a container which contains a piece of matter. As usually we can have two views of it. We can look at it as a macroscopic body, or we can describe even the macroscopic properties of that system by our knowledge of a microscopic property. And quite remarkably, when thermodynamics developed, people had very little knowledge of what is actually inside, how is the internal structure of the materials. The concept of atoms was, of course, hanging around since the time of ancient Greeks, but I gave you an example of a Gassendi, that he used to think about the atoms as being different atoms for heat and cold and so forth. So that microscopic story was very vaguely understood, to say the least. But the macroscopic physics was pretty well understood. And people had developed most of the thermodynamics on a phenomenological level. And it turns out that actually those laws of thermodynamics, which we now understand on the basis of a microscopic physics very well, they have been first derived from a macroscopic observations and with the use of a very deep logical thinking and analysis. It is particularly true as related to the second law of thermodynamics, which will be the subject of our talk next week. But because we have to devote probably all the lecture to the second law, because it's the fundamental, in some sense, law for biology. And the second law is now, of course, understood and discussed on a completely different way than it was 70 years ago. But still, when I was a student at the university, what we were being taught was a phenomenological thermodynamics. And we were learning the first, the second law of thermodynamics without any relation to the microscopic structure, and particularly, and I now use for the first time the word, without the probabilistic aspects of it. But we have a piece of matter and it consists of a particle. So let's concentrate on what those particles out of which the body are doing. Well, we already were discussing that in the liquid and the gas case, they are moving. So I described that they are moving, so they have a kinetic energy, a relation to the velocity, which I have denoted as a red arrows. And they move, of course, at random. So we have touched this probabilistic description by discussing a diffusion. So that's one aspect of the motion of those particles. But we know that if they interact by the forces between themselves, and we know that if there are very few of those particles, like in a gas, they are so far away that the interaction between them can be described as a collisions. But if they are much denser, like in a liquid, then the details of that interaction is of some importance. And I have shown that interaction by that picture, cartoon, P-like picture of two particles with a spring between them. So we have the energy of a mutual interaction of those particles out of which a block of matter is built. Well, because they interact with each other, then eventually that interaction, or occasionally, that interaction may become so strong that those particles form a compound. They are having a bound state. They stick together. And that I have shown in here. And then if they are tied to each other by the intermolecular forces, then there is an energy stored there, and that energy can be liberated when this binding is broken. That is a chemical energy. This is a chemical energy which is so important in biological processes, namely in which most of the energy in the human bodies in our tissues is concentrated. But there is also another aspect of the energy, namely that if I have a molecule, that this molecule, which might consist of many, many atoms, for example, a molecule of a protein consists, and you might correct me, but I believe I'm not making a big mistake. The protein molecules might have millions of atoms in it, millions of particles in it. So if they have a million of the particles, they hardly are rigid objects. They can move. So there is an energy related to the vibration and conformal changes of those molecules, which is another container of the energy in our piece of matter. Well, if there are atoms there, then we know nowadays that atoms consist of a nuclei and electron clouds around them, and that electron clouds around those nuclei are governed by the laws of quantum mechanics. But we also know that this law allowed the electrons, in this language of the 19th century, change their orbits, namely to fall from the higher energy state to the lower energy state, and then emit photons, emit the light, emit the radiation. And if they emit the radiation, then there is another part of an energy which comes out in our body, which is electromagnetic radiation. And I can shine in my material body electromagnetic radiation. So I showed that the contribution of electromagnetic radiation by that part of a cartoon. So I have two parts of it which are related to the electromagnetic waves. And finally, we learned at the turn of the 19th and 20th century that the nuclei disintegrate, that there is a phenomenon which is called radioactivity. We deserve it to the Maria Skłodowska-Curie, her husband, and the mentor, Henry Becquerel, that there is a radioactive decay. So the nucleus disintegrate, and when it disintegrates, it releases energy, and it releases energy in three different kinds. It releases the kinetic energy in a form of a very heavy particles called alpha particles, which are nothing else than the nuclei. I'm terribly sorry, but I lost the connection. So we had this box, and the radioactive decay creates the particles which are nothing else than the nuclei of a helium-4, consisting of 2 neutrons and 2 protons. But the other kind of energy emitted from the form of the energy which comes out from radioactive decay is a beta decay, which is the kinetic energy of a very fast electrons ejected in the process of the disintegration. And finally, we have again electromagnetic radiation, very short wavelength waves, electromagnetic waves, which is usually called gamma rays. So that is basically what kinds of energy are all inside of it. So when we have two pieces of matter, and when we connect it with the other matter, in the process which we discussing a zero law of thermodynamics, and if the energy is transformed from one to a piece of matter to another, the processes are extremely complicated. We can, of course, try to do the microscopic calculation and go by one piece of type of energy to another and discuss what is happening, but that is not very fruitful procedure. And in addition, the energy can transform into each other within our body. The disintegrating radioactive nuclei had initially a certain energy, and this energy which was a binding energy of a nucleus, is now released in the form of these three types of radiation I have tell you. So the energy can change. But the one property of that is that it cannot be lost and cannot be created in that process. So if I had my nucleus which disintegrate, it might produce the alpha particle or beta particle or gamma ray, but the energy is conserved. The total energy cannot be changed. And therefore, if I had that just split in two pieces of energy, I have the combination of it. So the sum of all the energies within my body must be constant. And the sum of that energy is called internal energy, and the internal energy of the body is usually denoted as a capital letter U. All right, so we know that we have that body, and now let's look up and remember that energy is conserved. So this is also the point where I have to make a comment that you might have heard that there are people who are claiming that we should go on from the that we should change our civilization in order to use a renewable energy. Well, that concept is completely without sense, physical, because energy cannot be lost or renewed. It's conserved. And the only problem is that we have to understood properly what is meant by the conservation of the energy. So we have our body again, and let's see what is happening when we contact the body to another body. For example, when we apply an external force. Well, let's first study a simple example. We have a gas, a container with a gas. We have a piston on the one side of that container, and we can apply a force to the piston, the force F, and we shift the piston a little bit by a distance delta x. What we know from physics is that that force applied to the piston results in the internal pressure of the container, and that this pressure is related to force simply by the multiplying by the area of the piston. But if the piston moves a certain distance delta x, then this force does a work, and the work is a force times a distance. So the work is a pressure area times delta x. But what is the A times delta x? This is nothing else than the change of the volume of the container, and therefore the work done by our external force moving the piston is equal to a pressure times the change of the volume. Let's look at that formula carefully. Work is just how much energy we have added to the system. Pressure is the intensive quantity. It does not depend on the number of atoms or anything. And what is the volume? The volume is an extensive quantity. If our container with the piston will be 6 times larger, then the work will be 6 times larger, but not because the pressure has changed, but because the volume has increased. So the work done by our force, the energy which we have pushed into our system, depends on the intensive quantity called pressure and the volume. And we know that the pressure and the volume are connected by the equation of state, which we were studying some weeks ago. So we have now we can envisage that there must be a general rule that if we apply a force which connects within a given plethora of possible types of energy within our body to one of those particular kinds of energy, then we must find a corresponding pressure, intensive parameter, which controls that interaction. But in general, we always will have the situation like this, that the work done by external perturbation of a system will be something like this relation, pressure times change of volume. Of course, there will be different units of this quantity. They might be different quantities, but they always will have the same property, that one of them will be independent of the size of the system, be intensive, and the other will be extensive quantity. And we will be discussing that in a concept of the first law of thermodynamics in a greater detail next week. And then we will go on with the second law of thermodynamics. Thanks you very much. And as usually, I will provide the recording to Dr. Dziwek. Dziękuję.